we're going to do some more GCDs here, and we're going to do this so that when we do the Euclidean algorithm in class, we'll understand why it works. So I'm going to force you to compute the GCD of two more numbers, and then, well, maybe two more pairs of numbers, and then we'll stop doing this. So I've got these two pairs of numbers here. I'm going to let you guys stop and do the work. It's good practice. I'll go ahead and give you the factorization without doing all the steps. So we get 2 squared times 3 times 5 cubed times 11. And then this number factors as 2 times 3 times 11 times 13 times 29. So the things that they have in common are a single 2, a single 3, and an 11. So the GCD should be 2 times 3 times 11, which is 66. Okay. So now we're going to do something that looks a little strange, but this is actually going to be the first step of the Euclidean algorithm. And we don't have to worry about what the Euclidean algorithm is exactly yet, but I want us to talk about this so we can see why it's going to work when we get to class. So what I want us to do is I want us to take the bigger of these two numbers, the 24,882, and write it, essentially find the remainder when I divide it by the other number. So I want to write it as 16,500 times something plus a remainder. And so this remainder is behaving exactly like when we did modular arithmetic. So if I divide 24,882 by 16,500, I get 1.508. So what's going to happen here is that my Q is going to be the whole number that I got there. It's going to be the 1. So I'm going to have 24882 is 16500 times 1. I'm going to keep the 1 there because when we do the Euclidean algorithm, that'll be useful. And then I have to figure out what the remainder is. Well, now I can just do 24882 minus 16,500 times 1. And that gives me a remainder of 8382. Okay, this is going to be the first step in the Euclidean algorithm. Okay. And now what I want us to do is I want us to look at the GCD of these two numbers, okay? So I'm looking at the GCD of my original smaller number together with the remainder, okay? So I'm looking for the GCD of 16500 and 8,382, okay? We already know the factorization of the 16,000. That didn't change. And if I give you this factorization, let's hope that I wrote it down somewhere. This ends up being 2 times 3 times 11 times 127. I'll let you verify that. And 127 turns out to be prime. Okay, so if we ask ourselves, what do these have in common? They have a single 2 in common, a single 3 in common, and a single 11 in common. Interestingly enough, that's the same thing that we saw before. So the GCD of this pair of numbers is still 2 times 3 times 11, which is 66. Ooh, that's interesting. And these two are equal to each other. Okay. So here's an interesting fact is that when we rewrite, like when we do this rewriting, the pair of like smaller numbers has the same GCD as the original pair. And so this is why the Euclidean algorithm is going to work, because what we're going to do is we're going to like keep replacing our original pair of numbers with pairs of smaller numbers, and the GCDs are going to be equal all along. So as we break this down, we're not actually changing the GCD. The reason why this is true is because essentially, when we look at both sides of this equation, we're saying that like the biggest number that divides like all three of these numbers is the same. And that's really because of this equation, like to make it equal, we have to have something that kind of divides all of these numbers in the same way. Otherwise, these two sides of the equation wouldn't be equal. So that's essentially where that's coming from. Okay, so that fact's going to be crucial when we use the Euclidean algorithm. You can do the Euclidean algorithm without knowing that fact, but I think we'll refer to that in class. So that's why it's useful that we saw this. Okay, so on your own, before class, go ahead and practice these three here. So find the GCD of these pairs of numbers, show all your work, make sure you're showing me your prime factorization. And then in class, we'll use the Euclidean algorithm, which will just be kind of a little more systematic way of solving these.